Hi guys, welcome to the second problem on the Stat 110 Midterm 2017 solve. Again, I encourage you guys to go and solve this midterm before you come and watch this video so you can get nice and emotionally attached to the problems and it will hopefully be a better time then. So problem 2, it's a chicken egg looking problem. And we have two proofreaders, Prue and Frida, and they have different probabilities of catching the mistakes. So let's see. So Prue has a probability of P of catching a mistake, and Frida has a probability of of F of catching the mistake. And they don't catch it with probability 1 minus P and 1 minus F. All right, so we have a book that has n typos, and either the book gets assigned to Prue or it gets assigned to Frida with equal probability. So 1/2 probability it gets assigned to Prue and 1/2 probability it gets assigned to Frida. And we want to find the distribution of the number of typos that it gets detected. All right, so this is starting to look a lot like the binomial. So in particular, if we are assigning the book to Prue, then it's going to be binomial n comma p because we have n trials and the n trials are the different typos. And they're independent because it says in the problem. And Prue has a probability P of catching each typo. So this is our success probability just for Prue. So we can say let's call the number of typos found T, big T. Big T is number of typos found. And say the event that we assign it to Prue is B. Then we can say what I just said as T given B. So number of typos found given it is assigned to Prue is distributed binomial n comma P. And with a similar argument, we can see that number of typos found given it's not given to Prue is binomial n because we still have n typos, but this time it is going to be F because the probability Frida finds a typo is F. All right, so we have this isn't going to be binomial itself, unconditional on who it's given to, since there's a 1/2 probability it's Prue, 1/2 probability it's Frida. An edge case might be like Prue always finds the typos, so P is 1 and Frida never does. And then it averages out to half of them being found, but it's not going to be quite like that. The distribution is going to look a little more bimodal. It'll have like 2 humps in the PMF. So we can write this out using LOTP. So the PMF which is one way we can define the distribution, is going to be, let's do some iPad magic to give myself more room. It's going to be probability T equals little t is going to be equal to, via the law of total probability, PMF conditional on B times probability of B plus PMF conditional on not B times probability of not B. And these probabilities here are both 1/2. So this is going to be 1/2 times conditional PMF conditional on B, which we know is binomial NP. So we're going to have the binomial PMF there and choose T times P to the T, and then Q to the N minus T, plus 1/2 times N choose T, F to the T, and G to the N minus T. And this is the PMF. We have to define the support because that's very important. And the support is going to be anywhere from 0 typos to n typos. Since we can catch anywhere from 0 to n typos, the support of each one of those binomials is also 0 to n. So t can equal 0, comma, dot, 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 n. So that's our support. And that's part A. So moving on to part B, another book is being written. And when a draft of the book is complete, it will have a Poisson lambda number of typos. So let's say, yeah, so Poisson lambda number of typos, and Prue gets the book this time for sure. There's no Frida anymore. Prue catches each typo with probability P. All right. So this is like exactly chicken egg, where we can see the typos themselves are the eggs, the number of eggs that the chicken are laying, and the probability the egg is hatched is P. And in this case, a hatched egg would be Prue catching the error. So the number of, so let's look at what we're actually solving. The probability that Prue catches exactly K typos, given that she misses exactly M typos. Okay, so that's going to be, let's give these names. Say X is the number of typos caught, and Y is number typos missed. So unconditionally, this is going to be chicken egg. We know that X, number of typos caught, that's going to be distributed as Poisson P lambda by chicken egg. And the other way around, the number of typos missed, that's like, now a hatched chicken is going to be a typo not caught. That's also going to be Poisson, but this time the probability it's not caught is 1 minus P Q lambda, and also chicken egg. All right, so let's write out what our probability is. We are, or let me make this smaller. Oh no, Prue came in there with whatever. Prue. All right, so we're looking for the probability X is equal to K, or I like using little x. X is equal to little x. Oh, except in the problem it says K. So let's stick with K. X equals K given Y equals little m. Note that by the story of the chicken egg, this like Y is not, like these two are actually independent, and that's just chicken egg. So this is what we're looking for. Since X and Y are independent, this is just going to be equal to probability X equals K. And now we can just use the Poisson PMF, and that's going to be e to the rate, which is negative lambda P, since P lambda here, times the rate to our value K over K factorial. So this is our PMF. Now what's our support? Our support is, we can go, okay, so we have Poisson lambda. Poisson lambda's support is 0 to infinity, just the natural numbers. Same for Poisson P lambda. So our K can be 0, 1, 2, dot, 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 to infinity. And that's problem 2 on the 2017 midterm. Hope to see you guys on problem 3.